we're very happy to have Karina Batistelli today, who will tell us about Kazhdan-Lusztig polynomials for B2 tilde.
Thank you very much. I want to thank, first of all, again, everybody for the invitation and everybody who's here for coming to listen to this talk. And as Iva was saying, I'm going to talk to you about the Kazhdan-Lusztig polynomials for the affine value group of type B2 tilde. This is a joint work with Adam Bingham and David Plaza. And so the first thing we're going to do is we're going to have a very, very brief overview of what is known in the subject. Then we're going to move on to the definitions and the tools that we're going to use in this talk. And after that, we can move on to seeing what the actual formulas are for the Kazhdan-Lusztig basis elements in the three regions we're going to have for this case. And then we can use that as an example and find some concrete examples of Kazhdan-Lusztig polynomials from the formulas that we already have. And so these polynomials were defined in 1979, and they are very important in representation theory. Because, for example, if you have a complex semi-simple algebra, you can look at it from two different sides. You can look at it from the geometric side and study the sugar varieties, and you can look at it from the algebraic side and study the highest way representations. It turns out that the Kazhdan-Lusztig polynomials provide information about both, so they serve as a sort of a bridge in between the two words. And however, and even though a lot has been done in finding these polynomials, the cases where the explicit closed formulas are known are very little. In fact, for A1 tilde, this case has been known for all along. A2 tilde was described only in 2020 by Libedinsky and Patimo. And in the case that AN tilde, Libedinsky, Patimo, and Plaza worked on the pre-canonical basis. And with that basis, they found cases A3 and A4. And I think that those are the two cases they found. And for B2 tilde, we already know that this is going to be trickier because the W graph in this case is not locally finite. And that is going to make things more complicated. And we're going to see how. So I'm going to start with the first definitions that we're going to use throughout this talk. The first is regarding the val group that we will be working on. So this is type B2. So we're going to have.
Sorry to interrupt,
yes.
But in the affine case, it's still true that Kazhdan-Lusztig polynomials are Poincaré polynomials of intersection cohomology, some Schubert cells in an affine flag manifold of some kind.
I'm sorry. I am not the geometric person. You can ask that question. I don't know. I'm sorry. Okay. I'm coming from the algebraic world. I don't know a lot about the geometry. I'm sorry. So, well, if anybody else in this room knows the answer to this question, please go ahead and mute yourselves and please answer. Okay, so otherwise I'm gonna move on. And so we have this Associative group, which is generated by these involutions, S1, S2, and S0. I'm going to zoom in a little bit. And I've painted them in different colors for a reason. And we're going to see why in a minute. And so they have these relations that we can see right here. And as always, we're going to denote the length and the order, the broad order in the traditional way. And we're going to move on now to the Hecke algebra. So this is the unitive associative algebra on the Loren polynomials, and it has invariants V and V inverse. And the generators here are gonna match those of the Associative group. So we're gonna have one of each color as before, and the relations they verify are exactly the same. +1, which is this one that we can see right here. And so if we have a reduced expression in the val group, then we can write that element as the product of the generators in the corresponding order. And so these generators form a basis. This is called the standard basis of the Hecke algebra. But it's not the only basis that the Hecke algebra has. The other basis, in order to define the other basis, we need to define what a self-dual element is. So an element in the Hecke algebra is going to be self-dual if it verifies these two equations. And with that in mind, the second basis of the Hecke algebra is the Kazhdan-Lusztig basis or the canonical basis. And the elements there are uniquely determined by two conditions. The first one is that they have to be self-dual, which is why we get this definition right here. And the second one is that they should have a formula that looks like this. So I'm going to zoom in again. We are going to be having elements in the bio group that are lower or equal, even in the case of W, in the Broad order, and we're going to have a sum that looks like this. It's important that this guy is always accompanied by 1. And these guys are what are called the Kazhdan-Lusztig polynomials. And the last formula I want you to pay attention to is this one, because we're going to use it a lot. And so what we're going to do is we're going to grab an element of the val group, and we're going to sum over all of the elements in the standard basis, counting all of the elements that are lower or equal than W. And I'm going to multiply them by just some monomial. But it's important to notice that everybody who's lower or equal than W is going to show up in this sum. What are the main ideas of the proofs that I will be sharing with you today? So the first idea is this idea of the mu coefficient. There's two formulas of this. The one I'm going to show you is the case where the W is, when I multiply H, the Kazhdan-Lusztig polynomial, the Kazhdan-Lusztig basis elements HW by the one corresponding to another reflection, what's going to happen is, if I have two cases, if W is lower than WS, then I'm going to have this formula, and if not, I'm going to have another formula. But this is the one that we're going to focus on. And the reason is I'm going to be increasing, and I'm going to show you how in a minute. But this is the formula that I care about. And the way that we are going to use this is the following. If I find the formula of a Kazhdan-Lusztig basis element of one person, then using this formula, I can find the guy which is next to it, increasing, if it's increasing. And what I need to see is what is happening with the coefficient of V in the Kazhdan-Lusztig polynomials of the guys before. So I have this information available. If I got up to a certain point, I can move up one step at a time. So this is amazing. And the second kind of proof that I also love is using self-duality. So if I happen to find a formula of a person, and a formula that looks like this, so it's a sum of elements of the standard basis elements that are accompanied by polynomials, then the only thing that I need to prove in order for it to be a Kazhdan-Lusztig basis element is that it needs to be self-dual. So if I ensure that it's going to be self-dual and the formula looks like this, then it has to be an element of the Kazhdan-Lusztig basis. So that's what we're going to be working on. Now, the last thing I want to introduce before moving on is the geometric realization of W as the group of isometric transformations in the plane. What this means for us in real life is that we're going to have the plane divided in triangles. Each of the triangles are going to be matching the colors of the involutions, basically. So we're going to have a side which is red, a side blue, and a side green. And if I have an element of the val group, which is written down like this doesn't have to be a reduced expression, just has to be an expression. If I have it, then I can associate that element with an element in the plane by starting in the identity triangle, which is this yellow one, and crossing the walls of the colors that correspond to the involutions that show up. And so I'm going to identify W with this triangle in which I arrive. So this is a good way to keep track of what is happening in a more visual way. That's one thing I want to share with you. The other thing, which is going to make our lives way easier, is that we're going to have an automorphism that sends S2 to S2, so sends blue to blue, and it sends red to green. And what this means, for example, is that if I found the formulas of the north wall, This is the north wall. Then the formulas of the south wall are this automorphism of the north wall. So phi of the north wall is the south wall. So I only need to find the formulas of the north wall, and then I can apply the automorphism, and I automatically have the formulas for the south wall. So this makes our lives easier, just because of the way that the group works. And one more thing that's going on here is that we have these three regions. We have the region that we call the big region, which is the largest two-sided cell, which is this like 8 connected components that I'm marking here. This, in terms of the formula, is the easiest region. The formulas here are going to be the simplest. Then we have the thick wall. This is a bit more complicated. So we have the north wall, the south, the east, and the west wall. And definitely the hardest is the thin wall, which is northeast, northwest, southeast, and southwest walls. And that's way, way, way uglier. And you can actually see, I'm going to show you examples of how you can see that the W graph is not locally finite here in those walls. So we begin with the big region, the easiest region. And what we're going to focus on is these elements that I'm going to call thetas. These are the linear combinations of fundamental weights. And of all of the regions, I'm only going to focus on one, on the one that I call the favorite region. And once I have that region, I only need to find 3 more, but I'm going to get there in a minute. So the elements I want to focus on are these thetas, and the thetas are these triangles that you see here. So these are all thetas. These are all thetas going up. And the way we name them is this is theta 0, 0, theta 1, 0, theta 2, 0, and so on. Theta 0, 1, theta 0, 2, theta 0, 1, 2, and so on. So it's related to the fundamental weights. But as you can see, we're not covering the whole favorite region like this. And that is because each of the thetas has 3 friends. Has the best friend, has the second best friend, and it has the third best friend. And if we study the thetas and the 3 friends, we can actually cover the whole favorite region. And once we've done that, we can move on to the rest. Why? Because as you can see, for example, if I have, I'm going to use another color. If I have figured out what this is, then I can figure out what this is by just adding S0 in front of the element. And so by using the recursive formula of the mu, I can actually figure out what this other wall is. And the same thing is going to happen here, and the same thing is going to happen here. And so once I find the fundamental, my favorite region, I can move on to other 3 regions. And the other 4 that are missing are actually what is happening when I apply the automorphism. So those ones I have completely free. I only need to focus on 4 of them. The other ones are free. And so in order for me to finish the whole big region, I just need to start with the favorite region. Now, let me tell you how we're doing this. The way we're doing this is we are giving Sage, we're asking Sage for the formulas. And Sage is giving us back stuff. It's giving us back formulas that have a lot of standard basis elements multiplied by things. And these standard basis elements can show up all over the plane. And so what we ideally want to do in order to make this formula more accessible is write it in a way that is simpler, instead of just having terrible amounts of sums of things that you don't know what is happening. And one way to do this is using these n sub w terms. And so if we can group terms together and use just one term to group them all, then this is amazing. And this is what we do. And so it's important for us to understand what this means. which, if I, in the case I'm in right now, I'm in the case where W is theta mn. So I need to understand, first of all, how it looks like when I'm trying to understand what the set of the elements that are lower or equal than theta, what those look like, basically, in the plane. And the way we do that is, well, this is how they look like. I'm spoiling my own talk, but it's my talk, so it's fine. And so I'm going to share with you how we do this. First of all, it's worth noting that this is the picture for x lower or equal than theta. But if I put another W here, then the picture is going to change drastically. So this is not going to be the same. And second of all, the way we're going to paint this is we're going to start with theta m0, and then we're going to go on to theta mn. And I don't know if you recall this, but the thetas were these triangles that I am painting black right now. These were the thetas. And so the way we paint this is all of the elements that I am painting right now are all of the elements of the val group that are lower or equal than theta 0, 0. And if I want to know which ones are lower or equal than theta 1, 0, what I do is paint I add basically all the, I make the rhombus a little bit bigger. And if I want to know what theta 2, 0 is, I do the same thing. I add just the squares, and the same with 3 and the same with theta 4, 0. So this black one is theta 4, 0, and all of the elements that are lower or equal in the broad order than theta 4, 0. How do I move on to theta 4, 1? What I do is I attach all of the squares that are next adjacent to the drawing that I already had. So I have all of the ones before plus all of these squares. And if I want to find, this is theta 4, 1. And if I want to find theta 4, 2, I do the same thing. I attach all of the squares that are next to the picture that I already had. I expand the picture this way. And so what this is telling us is, again, how our formulas can be made easier, because I would be grouping all of these elements inside one n sub w. So that would simplify a lot the elements that show up in my formula. Now, this is what the formula looks like. And when I was saying that this is the easiest case, that's because the only n's that show up only contain thetas, not friends of thetas, not people from other regions, just thetas. And the thetas that show up are depending on these support sets. And this is basically very easy. This depends on whether m is even or not, but it's always the same thing. To the first coordinate, we subtract 2, and to the second coordinate, we subtract 1. And those are all the thetas that are going to show up. And so, for example, if I want to find the formula for the Kazhdan-Lusztig basis elements of theta 1, 1, I begin with 1, 1, and I subtract the second coordinate until I get to 0. So all of the people that are going to show up are those two, just those two. And I have another example. If I have the support of 2, 2, then I'm going to start with 2, 2. I'm going to subtract 1, and then I'm going to subtract 2 in the first coordinate. The only thing that's not valid is this guy because of this condition, but it doesn't really matter. It's just a condition. And so the people that are going to show up are those that are here. Now, what I want to show you here is the picture, how we draw these formulas in the plane, because this is going to matter in terms of how we find the formulas then. And so the way we're going to draw this is, my tablet is not liking this moment. So the way we're going to draw this is we're going to move on to the exact place where theta 1, 0 is in the plane, and we're going to paint that. And we're going to say this is also having the square there. And so I have to paint theta 1, 1, and I have to paint theta 1, 0, and those are the two who are there. And the same thing is going to happen on this other side. So I have theta 0, 0, theta 2, 0, and so on. So I just paint the one triangle that has everybody there. But remember that actually what this means is that the people from the val group that actually show up in this formula are, in this case, all of these people show up. And then all of these people, all of these people show up again. So when I'm trying to describe this formula, what I actually mean is that all of these people are inside of the formula, of this formula. This is just written in a way that it's simplifying everything. And the same thing is going to happen in this second picture. So how do we prove this? And this is where we get to my favorite part. I don't know if you people watch a lot of movies, but I'm going to make a very big movie reference here. And so the way we're going to prove this is we're just going to use induction. And this lemma is a lemma that is also proved by induction, so it's not hard to see. So I'm not going to get into that. But I'm going to prove this by induction, assuming that m plus n is lower than u. And then by inductive hypothesis, this person and this person and this person and this person are already Kazhdan-Lusztig basis elements. So they are self-dual, just by definition. And also this person is also going to be self-dual because it's a linear combination of self-dual elements. And so this poor guy has no other choice but to be Brad Pitt. It has to be self-dual. It has no other choice. There's no other way. So this is how the movie ends. I'm sorry, I just spoiled something. And this is the way we prove this thing. So it's pretty straightforward. And now that we have the formulas of the thetas, we can move on to the friends of the thetas. And this is also very simple to prove once that you have proven one formula, because what we're using here is the recursive formula. We know what the formula of the theta is. And so we can use this formula and study the mu's, and just with that, we can conclude what is happening with the rest of the friends of the thetas. And this is actually pretty easy because we just have one or two elements on the right-hand side of the formula. So this is still pretty manageable in terms of formula. This is pretty nice. Once we've done this, we can move on to the other three regions. The other regions were S0, C, S2, S0, C, and S1, S2, S0, C. And so in the same way, using the mu coefficient, we prove all of these formulas. So it's pretty straightforward. And with that, we have concluded all of the big region, because thanks to these four regions, we can use the automorphism and find the exact formulas for all the other four. We're going to move on now to the thick region. That's slightly more complicated, but it's okay. So the way this works is, again, we're going to have the north wall, the south wall, the east, and the west wall. And the elements of the north wall that I'm going to be thinking of are the ones that look like this. So I have red, blue, red, green, blue, green, red, blue, red, blah, blah, blah. So going on this path, these are the guys that I like the most. And we're going to have two things that are going to help us here. The first one is that, as I said before, the south wall is phi of the north wall. So I just need to find the north wall. And the elements of the west wall I can find using the recursive algorithm. And so I only need to focus on the north wall and on the east wall. And if I have those ones, then the rest is going to follow. The rest is going to be easy. I use the recursive algorithm here, and I use phi here. Phi, I don't know. I always say that wrong, I'm sorry. Again, what's going to happen is when we're going to ask Sage for the formulas here. And again, it's going to throw a bunch of elements showing all over the plane, and we want to try to figure out how we can group them in a smarter way. And again, we're going to try and do that by using n sub w's. And if you recall, the trick here was to understand the difference of length. The trick here was to understand what was in this set. And so W now is an element of the north wall. And what is happening in the north wall is that it's behaving differently modulo 3. So you can see here that if X is 3K, 3K plus 1, or 3K plus 2, the elements show up differently. So if I want to see what is happening, they are different. And just to have a reference, these are the elements located in the actual plane. And when we were looking at the formulas, again, if you find one, you can find the rest using the recursive algorithm. So we just need to find one nice formula for one of these people, and then the rest is going to work out. And the one that we like the most is 3K plus 1. That is our king. And it happens to be on the north wall. So I just call it Jon Snow, because I'm me. If you haven't met me already, you're meeting me in this talk. And so this is our Jon Snow. And this is the way that the formula looks like. And this looks a bit nastier than the other one, but it's not so much so. What we have here is we're always going to have two elements of the north wall, only two. We're always going to have one element that shows up alone, but changes the monomial. And we're always going to have these two elements that show up together. One of them is one of the east wall, and the other one is a friend of the theta. And I brought pictures. And so, as I said, I'm going to have two elements in the north wall. One element is going to show up alone, and the other ones are going to show up always in pairs. And again, two elements in the north wall. One element shows up alone, and the other ones show up in pairs. So if we're looking at this in terms of the picture, it's easy to keep track of them. So the formula is still pretty manageable so far. And notice here that before with the thetas, all of the formulas were contained in our favorite region. None of it was leaving the region that we were working on. But here we have elements of the thetas, and we also have elements in the north wall and in the east wall. So it's getting a little more out of control. So again, we're going to want to prove this. And the way we're going to do this is using this lemma. And here we have more information, because now we know that the thetas are actually Kazhdan-Lusztig basis elements. So using that, I can tell you that all of these people are self-dual. And I can also tell you by inductive hypothesis that this person and this person are self-dual. And this other person is also going to be self-dual because it's a linear combination of self-dual. And so this person has no other choice, again, but to be Brad Pitt. It has the shape of the formula that we want, and it has to be a self-dual element in order for it to be a Kazhdan-Lusztig basis element. So this is the ending of the movie. And now that we have found one of our favorite people, we can move on to the rest. The way we move on to the rest is, as usual, we use the recursive algorithm. And so you can see here that this is pretty easy. It has nothing on the right-hand side. And if we want to move on from 3K plus 2 to the next person, it gets a little bit more tricky, has more elements, but still the computation is pretty easy. We know the first person, we move on to the next one using the mu coefficient. We just need to figure out what the mu coefficient is. But then we just basically have found all of these formulas. And you can notice that these are a little bit trickier than the rest, than the thetas. Because in the thetas, we only had like 2 people on the right-hand side. We have 5 here. So it's a little bit uglier. And so let's have a closer look at this. We have these elements that I'm gonna put here are gonna be the Jon Snows. They're gonna be the kings of the north. These are the people that we have formulas for. We can also find 3K plus 2. So this one is an easy step. It needs nothing more. It just has the same, basically it's the same formula. And from now I can go to the right or to the left. And I'm always going to have the choice of crossing a red wall or a green wall. And that's why I have 2 formulas here. This one crosses the green wall and this one crosses the red wall. That's why I have more cases. But if you've been looking at what I've been doing, I've been sort of hiding something, which is the fact that I'm only working on this wall right here. And I've given them names. I've called them x sub n's and people and whatever. But I haven't said anything about these people. So technically, they are those that shall not be named. And of course, I call them Voldemorts. Of course, poor people. Like, how would I call them if not? Okay. So we have found the north wall. Thanks to our automorphism, we also have the south wall. And now we can move on to the east and the west. The east wall is also simple, but you can see here that we have elements that aren't just, again, they aren't just on the wall that we're working on. So this is phi of a theta, so it's still manageable. And the way that we prove the west wall is exactly using the recursive algorithm, and it's very easy. So once we have found and proven these formulas in the way as we did before, we have found the whole thick region. And we can move on to the last region, which is the thin region. And that one is a bit more tricky. Why is this one a bit more tricky? So we want to focus on the northwest. Oh, I don't know what the west and the east is, so I'm going to say it wrong. Northwest, northeast, northwest, I think, southeast and southwest walls. Those are the ones that awesome, I did it right. So yes. So I'm learning what east and what right and what left is still. So I'm going to focus on one of those. And I'm going to focus on this one, on the northwest wall. And these guys are also going to start to be more tricky because they are different. The people in the north wall were different modulo 3. The formulas even were different modulo 3. And these formulas are going to be different modulo 4. So that makes it already more difficult. And so, but I'm going to focus on this wall. And I'm going to focus on this wall. And with the phi, with the automorphism, I can find the other two. So I don't need to do anything there. And so I'm going to focus on the elements that are 4k plus 3. But it doesn't even matter. Now, it's time for you to brace yourselves, because the next picture I'm going to show you, it's not a nice picture. It's just drawn by me. It has a lot of stuff going on, but it's okay. It's not a big deal. We can come up with a formula, but it's a little bit nastier. Hello, this is the horrible formula. I'm going to show you a better example first. So this is what is happening. So far, we have been having only n sub w's showing up. And here, we were not able to group everything that was showing up. We were not able to group it only using n sub w's. So for example, we have n sub w's here, but these people are still going around. They don't belong to an n sub w. Neither do these people. They are parts of different n sub w's. So this is already more complicated. We can't just reduce this to the more simple case. And if we change, because we've tried, you can see here version 2, version 4 of our drawings and our attempts. But if we change the n sub w's, because you can also do that, instead of saying, I'm going to grab an element of the north wall, you can choose to grab another one and group things in a different way. But even doing that, we were never able to just group everything together using n sub w's. There's always people showing up all over the place. And so the way that we found easier to do this was to define these other elements that I'm going to show you in a minute. But you can see already that this is way out of control because we have people all over the place. We have people like in all of the walls. And they show up like forever. As we go on, they keep showing up. It's not that they're changing places. They keep showing up more and more and more. And this is the wall that you can actually see that the W graph is not locally finite. Because what is happening is people keep showing up. I'm going to move on to that in a minute. But first, I want to show you the formulas. This is when you go to the dark side and it's very difficult to come back to the light because it's horrible. So, but it's, poor thing, it's what it has. So before, remember that we only had n sub w's showing up. Now we're going to have n sub w's, but we also have these d's. These d's are just basically a truncation of an n. We grab an n and we truncate it, and that's a d. But we also have these u's that are just an n plus a truncation of a different n, which is given by the automorphism. And so it's weird what is happening. But so you can see that the formulas here, we have n's, we have d's, we have u's, we have people showing up that are just there. They're just Kazhdan-Lusztig basis elements. So this is very hard to like put very nicely in terms of n sub w's. And you can see here also how big things can get in terms of the sums that show up. And so we have conjectured these formulas, but we weren't able to prove them because the methods that we were using so far were we were doing things by hand, like we're putting one picture on top of the other and we can see whether there's an intersection of things. But here, when the sums get so big, it gets a little bit more out of control. So we cannot use the same methods. And we have tested this in Sage and it works up to k equal 5. And after that, Sage doesn't answer anymore, just doesn't want to give you like anything anymore, just says bye and stops working. And so, but if you find one of them, which is this, let's assume that this one is correct, then you can also find what is happening on the rest of that wall using the recursive algorithm. That thing you can actually do. But again, it's very hard to prove because you have a lot of sums here. And before we just had 2 people on the right-hand side or 5. Now we have just entire sums. And as we grow in numbers in k, the same thing happens with the sums. So if this were to be k equal 20, then the sum is going to be big. So it's hard to prove this. But you can actually do that. We can actually like sort of guess what is happening. And once we have found the northwest wall, we can find the north-southwest wall. And the other 2, thanks to the automorphism, are clear by definition. And so what is happening? So what's happening is that you can see, I want to show you here how we can see that the W graph is now locally finite. So the definition of it not being locally finite is that the mu coefficient, that there has to be a u, an element u, so that the mu coefficient is different for infinitely many w showing up. And the way we see this here is, for example, if I have this person, which I'm going to call West 4, because it's in the west wall and it's number 4. Starting from the identity, it's number 4. So this person is always going to have a mu coefficient 1. And so the mu coefficient was the coefficient that accompanied v. And so if I look at the west 4, the person West 4, it's always going to have mu coefficient 1 in all of these pictures. Not only in these pictures, but in all of the pictures showing up forever. And so I can actually say that the mu coefficient of West 4 in D 4k plus 3, this is a lie, plus 3 is going to be 1 for all k bigger than 1. And so we have found infinite many w's such that. But not only that, this is just for that person. But if I were to change and pay attention to these people that are also going to show up all over the place, these people, and they show up from here on forever, then I can actually say that these people, I can change that and say these people, and they are going to show up for every k bigger than 2. And the same is going to keep happening. We're going to keep finding infinite many things that repeat themselves. Because when we move on from one picture to the next, everything stays there, but we keep on adding stuff. And so that makes, and all of these people have mu coefficient 1, because everything has a v multiplied by them. So I have found like infinite examples of how crazy this bit is. And okay, so this is for the last part. We have conjectured the formulas for the thin region. And the last thing I wanted to show you, I may have gone too fast, but doesn't matter.
Right,
Yes.
could I ask actually a question? Maybe
Right.
I could wait till the end of your talk, but like this, are you saying that these like pictures stabilize? So there's D sub 4K plus 3. Could you say that this has some kind of limit as K goes to infinity?
I
mean-
don't think, no, I think that the formulas explode as K grows bigger and bigger. We keep having more and more and more things showing up. All of the stuff that was showing up to that K is going to show up and more.
But okay, so you have these elements which are like color coded like green and yellow.
Mhm.
And I guess those things by themselves also represent big linear combinations of H's.
Yes. Yes.
But if I ignore that, if I just say, if I don't expand in terms of H's, if I only sort of write things in terms of these like green and yellow, you're saying that more things show up, but do those things that show up occur far away from the origin?
Yes.
Okay.
What is happening is we keep going further away. So if
Okay.
I didn't have a picture like big enough, but
Mhm.
these people, I'm gonna delete some of it to make it clearer. But these people are gonna keep showing up all along this line. So you can see that we started with one person here, and then you have 3 here, and we have 5 here. But as this goes on, so this is the element that we're working on here. And so as this element grows, starting from that element, all of the people following that line are going to be the ends. So as you go further along that line, everything is going to follow you. So you're going to keep having more and more and more and more stuff.
Okay. Thanks.
Awesome. And compare this to, let me see, this picture of X something that, yes, stuff keeps growing, but it doesn't grow that drastically. You always have 2 people on the north wall. You always have one person that shows up with a different coefficient, but it's always showing up in the same place. And these grow in 2s, but you're just gonna add 2 elements from one picture to the other. And what is happening in the thin region is just way out of hand. You add a lot more stuff, a lot more stuff added to the ones that you already had. And so here you're moving direction sometimes compared to the thetas, but here in the thin region, you just keep having stuff popping up. And yeah, you can see that the D's are also showing up more along when we go like down and up and stuff. Thank you very much. So not for the question. So this is the last thing that I wanted to show you. And this is useful because basically you have the formulas, but you have the formulas of the Kazhdan-Lusztig basis elements. So if you were to want to find the formulas of the Kazhdan-Lusztig polynomials, you just need to look at the formulas and figure out where is the standard basis element that you want. And once you have found that, you need to like add all the people that show up and say, okay, so this is the polynomial that accompanies it. So it's hard to keep track of where these people are. And so the picture helps a lot. So what we want to do in this example, for example, is inside of the formula of theta 2, we want to know what is the polynomial that accompanies the standard basis element x11. And so I have written down here the formula that we had. And so basically what we want to do is we want to figure out in which of these we have x11 showing up. And so what we need to understand is, if you recall, the formula was this. So we had a length difference here. So we want to figure out if x11, which is the x that we care about, is lower or equal than the thetas that show up in this formula. And this is, again, the easiest case because we're working only on thetas. But I want to show you how you can do that with the pictures. Because we have drawn before how the elements look like. And this is this picture. So for example, I have marked here where x11 is. So the way that I can figure out whether x11 lives inside of one of these people is that whether it's inside the actual picture or not. If it's not inside the picture, then it's not inside this set. So for example, I'm going to start with theta 0, 0. And I said that the elements of the val group that are lower or equal than theta 0, 0 are these people. So x11 is outside. So x11 is not going to be lower or equal than theta 0, 0. So it's not going to be here. We're not going to have any standard basis elements in there of x11. And we can move on now to theta 2, 0. So the picture here of all the elements in the val group that are lower or equal than theta 2, 0 are these people. And here again, x11 is outside. So x11 is not inside n2, 0. Now, what we did to find n2, 1 was we needed to paint this side. So what we're going to do is going to paint all the squares that are adjacent to the picture that I have. So these are all the people that are lower or equal than theta 2, 1. And here we do have x11. So x11 is inside this formula. And of course, if it's inside this guy, it's also going to be inside the next person, because we keep on adding stuff. So it's also going to be inside theta 2, 2. And we can see that in there. So x11 is also going to be in theta 2, 2. What we want to know now is whether this is inside theta 0, 2, which is the one that is left. So again, we start by painting theta 0, 0. I'm going to paint now what theta 1, 0 is, which is adding all the squares adjacent to that. And what I want to know is actually theta 2, 0. So I'm going to paint again. So I'm going to add these persons here. But as you can see, x11 is not inside of this. So looking at this, the only two ends that have x11 inside are n2, 2 and n2, 1, theta 2, 2 and theta 2, 1. So now I can actually focus on finding the actual formula. So let's do that. So this is, as you can see, we can use this formula. So here the W is theta 2, 1, for example, and the length of theta 2, 1 is 14. So what I need to do is 14 b to the power of 14 minus 11, which is the length of x11. And I need to add this v squared, so plus 2. And so this is what the monomial is in the case of theta 2, 1. And in the case of theta 2, 2, the monomial is going to be the difference in length of theta 2, 2, which is 18, and x11, which is 11. So the actual polynomial is going to be b5 plus b7. So this is way, way easier than trying to figure out, like in an algebraic way, inside of whom we are living. Like this is very hard. And so the pictures have played like a very important role in our lives, trying to understand what was happening here. And I think this is everything that I wanted to share with you. So if you are curious about any of this, and if you want to see like more pictures, and if you enjoy painting mandalas or whatever, feel free to look at the paper. It's already in archive. And if you have more questions and you come up with questions after this talk, I'm more than happy to keep discussing this because I'm very happy about this. And so thank you very much for your attention.
Thank you for the interesting talk, Kari.
Thank you very much.